we meet again in the next session of the chapter 2, which is thermodynamic property relations. So for the first from the previous session, we have basically learned on the Gibbs free energy and the definition that relates around it. So for this session, I would like to start with the exercise, which is on hypothetical process path. Okay, in the comment section down below, please determine the enthalpy of the simple process below by using hypothetical process paths, whereby from a substance of A in solid condition, 1 atmosphere at 50 degrees C, to A in the form of vapor and 1 atmosphere and 110 degrees Celsius. The melting point is 60 degrees Celsius and boiling point is 95 degrees Celsius. Okay, so basically, of course, you can use the definition of enthalpy, which is the simplest one, which can relate with the CP or CV or C. CP or CV. Yeah. So these are the hints. So of course, you have temperature, you have the temperature, and you can calculate it, and then give the answer in the comment section down below. Okay, okay, this one we have done already. It's okay. Okay, we move on to the Clapeyron equations. So basically, what is a Clapeyron equation? Clapeyron equation is the third Maxwell relation, which is P per T and equals to S per V. And during a phase change process, P equals to pressure saturated, which depends on temperature only, is independent of the specific volume. So we can understand that pressure of saturated equals to the function of temperature of saturated, and the partial derivative P per T towards V can be expressed as a total derivative of dP per dt of saturated equals to the slope of the saturation curve on a PT diagram at the specified saturation state. So if you can refer to figure 4, so this one refers to the partial derivative P per T to V, which can be expressed as the slope of this. And then the slope is independent of the specific volume, thus it can be treated as a constant during the integration of above equation between two saturation states at the same temperature for an acetylmole liquid vapor phase change process. For example, the integration we're going to yield as follows, or this one. So if we rearrange it, it's going to be like this. So these are the important equations that you can relate to the Clapeyron equations, especially at the saturation conditions. Okay, during this process, the pressure also remains constant. Therefore, from the equations, so we can rearrange into dH equals to dds plus vdp, whereby the P remains constant. So we can remove this second term, and then we can only have TdS, which can also define as HFG equals to TSFG. Substituting this result into this equation, so we obtain dP per dt equals to HFG per TVFG, which is known as the Clapeyron equation, whereby the pressure has to be constant. And the Clapeyron equation enables us to determine the enthalpy of vaporization, which is HFG, at a given temperature by simply measuring the slope of the saturation curve on the PT diagram and the specific volume of saturated liquid and saturated vapor at the given temperature. So this is a general form of the Clapeyron equation when the subscript I and 2 indicates the two phases for easier visualization. So we can see here that this one should be derived from the slope of the saturation curve equals to HFG per TV. Okay, so the Clapeyron equation can be simplified for liquid vapor and solid vapor phase changes by utilizing some approximations whereby at low pressures the Vg can be approximated V to Vfg equals to Vg, treating vapor as an ideal gas whereby V equals to RT per P. I'm substituting into Clapeyron equation, which is this one, so we can get dp per dt. So we substitute the v, rt per p, right? So we can get this one, and then we rearranged it so we can get this one, integrating between two saturation states. So we get ln P2 per P1 saturated equals to HFG per R 1 over T1 minus 1 over T2 saturated. This is called Clapeyron closures equations, whereby it is simplified for liquid vapor and solid vapor phase changes by the approximation at low pressures and treat the vapor as an ideal gas. And the Clapeyron closures equation can be used to determine the variation of saturation pressure with temperature, and it can be also used in the solid vapor region by replacing HFG by HIG, the enthalpy of sublimation of the substance. Okay, we have some simple exercise by referring to this equation. Okay, we get the vapor pressure of a substance is 21 torr at 300 Kelvin, and calculate the vapor pressure at 310 Kelvin if the enthalpy of evaporation is 24 kilojoule per mole, and explain the trends. Okay, so in the comment section below, please give your answer and explain the trends. So I would advise for you to compile everything, and then you can just give the comment in one post. Okay, next exercise is the vapor pressure of a substance is 30 torr at 250 Kelvin. At what temperature will the substance have a vapor pressure of 150 torr? The enthalpy of vaporization is given at 45 joule per mole. So you should be able to use this intended equation. Okay, next one is the general relation for du, dh, ds, cv, and cp. The state of a simple compressible system is completely specified by two independent intensive properties like previously discussed. It is able to calculate all the properties of a system U, H, and S at any state once two independent intensive properties are available. And the calculation of these properties from measurable ones depends on the availability of simple and accurate relation between the two groups. And development of general relation for delta U, delta H, delta S in terms of P, V, T, and CP, CV, the properties values at specified states can be determined only after the selection of a reference state, the choice of which is quite arbitrary. Okay, by using this equation and the explanation previously, so please relate the S in terms of T and V, and relate S in terms of T and P, and relate du in terms of T and V, and relate dH in terms of T and P. You can use Maxwell relation and fundamental property and the definition of heat capacity to get this final relation. Okay, in the comment section down below, you can give your no, I think it's more convenient for you to give your answer in the Putra Blast, because you have to do some symbol that is you cannot interact in the YouTube. Okay, so I will open the link link in Putra Blast, and whereby you can submit by any time before next week. Right? Okay, internal energy changes, and consider U equals to U to the function of TV, and take its total differential, which is du equals to derivative of u per t to v dt plus derivative of u per v over t dv using the definition of cv. So basically we have du equals to cv dt to replace this one, and plus du, this is the same, and consider the entropy to be a function of t and v to s to the function of t and v, and take its total differential, so we can get ds. We change this dv to ds, v to the to s. Sorry, I think this is, sorry, this is u. Sorry, this is u. Sorry, this is not s. Okay, so we change everything into s. This one, u to s, and then substituting this into the TDS relation, whereby du equals to TDS minus P dV is going to yield du equals to T, and this one as follows. So this is when it comes to internal energy changes. And equating the coefficient of dt and dv in equation 1225 and 1227 give this equation below. And by using the third Maxwell relation, we can get this. We can get this correlation. So this one, after we have rearranged it, so we can get, and we can relate with the third Maxwell relation, so we can get this definition, especially for this one. And substituting this into equation 1225, okay, 1225, so we obtain the desired relation for du, whereby this is the delta u general relation, which defines the internal energy changes. Du equals to dv cv dt plus t minus t derivative p per t over v minus p to the function times dv, sorry, over dv. So the change in internal energy of a simple compressible system associated with the change of system of state from T1 and V1 to T2 V2 is determined by the integration of this equation 1229, whereby we can get U2 minus U1 equals to integration of CV and integration of this one. So basically, in thermodynamics, it will involve a lot of integrations so that you can get this answer. Okay, so that's all for this session. I will proceed with the next session with enthalpy changes and entropy changes. Okay, we have another 3. All right. Okay. Thank you.